All right, this is our second video for section 6.4 where we're looking at several trig properties. In this video, we're going to look at reciprocal and quotient identities, and then Pythagorean identities, as well as even and odd properties for trig functions, okay? And all of these properties can just, if you know them, they can help make evaluating functions, trig functions, a lot easier for specific angles, okay? So the reciprocal identities are really nothing new to you, okay? We know that secant is the reciprocal of the cosine function in terms of their ratios, right? So you can think of secant of theta as the same as 1 over cosine of theta. Cosecant is the reciprocal of the sine function, so cosecant of theta is 1 over sine of theta. And cotangent of theta is the reciprocal of the tangent function, so 1 over tangent of theta, okay? Now, where these three identities I think are extremely important and will come into play a lot is when you're evaluating any of these three functions, secant, cosecant, or cotangent, on your calculator, okay? You must use these when evaluating secant, cosecant, and cotangent on your calculator. So what I mean by that is let's say you're trying to find a secant of 30 degrees, okay? There's no way to reason that out by hand and get an exact value, so you'd want to approximate it on your calculator, and the calculators don't have a secant button programmed within them. Instead, you would have to type it in as 1 over cosine of 30 degrees to get your approximation, okay? All right, quotient identities, all right. We have two of them for the tangent and cotangent functions, okay? They can both be written in terms of sine and cosine. So tangent, we know, is y over x, right? And think about in the unit circle approach, sine of theta is equal to y, and then cosine of theta is equal to x. So that means tangent of theta can be thought of as sine over cosine. Okay, let me give you another proof that works for all values of r. So sine of theta is y over r. Cosine of theta is x over r. So that's the same as y over r times the reciprocal r over x. Notice how those wipe out, and you're left with y over x. Okay. Now cotangent of theta, its quotient identity says that it's equal to cosine of theta over sine of theta. Okay, and the proof of that would be very similar. Cosine of theta is equal to x over r. Sine of theta, y over r. It's equivalent to x over r times r over y. R's reduce away, and you're left with x over y, which is what we know cotangent to be defined as. Okay, so let's utilize some of these identities in these examples here. Find the exact values of the remaining trig functions given that sine of theta is equal to -4/5 and cosine of theta is equal to 3/5. Okay, so one way you could approach this, I know secant of theta is equal to 1 over cosine of theta, which is 1 over 3/5 in this case, and 1 over 3/5 is the same as 5/3. Okay, and of course you wouldn't necessarily have to show all that work. You can just jump right to the reciprocal and give you 5/3. It would be the same for reasoning for cosecant. That's 1 over sine, or 1 over -4/5 in this case, so that's going to become -5/4. All right. Now for tangent, quotient identity, and think of it as sine over cosine. Well, sine we know to be -4/5. Cosine we know to be 3/5. So this is going to give me -4/5 times 5/3. 5's reduce away, you're ending up with negative 4/3. And then cotangent, I could take, pretty much the same approach. Think of it using a quotient identity as cosine over sine. So that's 3/5 divided by negative 4/5, which is 3/5 times negative 5/4. 5's reduce away, and you're left with negative 3/4. Okay. All right, moving forward. Now let's look at Pythagorean identities, okay? There are three main Pythagorean identities, and if you know the first one, you should be able to derive the other two pretty quickly, okay? So let's say I am working with sine squared of theta plus cosine squared of theta. All right, now understand the notation there. I read it as sine squared of theta, but the order of operations would actually say you'd evaluate sine of theta first, and then whatever that result is, it gets squared. Okay, so understand the written notation is kind of misleading there. Sine squared of theta means plug a number in for theta, evaluate sine for that angle, and then square the result. Okay, well, if you're taking sine squared of theta and adding that with cosine squared of the same angle theta, Pythagorean identity says that always equals 1, okay? 1 plus tangent squared of theta is equal to secant squared of theta. And then 1 plus cotangent squared of theta is equal to cosecant squared of theta, okay? Now I mentioned these second two Pythagorean identities, they can both be reasoned out off of the first one pretty quickly, okay? So for example, let's say I took sine squared of theta plus cosine squared of theta equals 1, and I divided both signs by cosine squared of theta. Okay, what that's going to lead me to is sine squared of theta over cosine squared of theta plus cosine squared of theta over itself equals 1 over cosine squared of theta. Okay, and then simplify that. Sine squared over cosine squared, you can use a quotient identity on that, and you can say that that is equivalent to tangent squared. Cosine squared divided by itself is equal to 1, and then 1 over cosine squared is equal to secant squared. So ultimately, right here, this is going to lead you to this identity, okay? And I could reason out the third identity if I just took sine squared plus cosine squared of theta equals 1 and instead divided it all on both sides by sine squared of theta. Okay. All right. Now, last properties we're going to look at are the even and odd properties of our different trig functions, okay? So recall we looked at even and odd functions earlier in the course. For a function to be even, when you evaluate it with the negative of a value, it should result in the same thing as if you evaluate it with the positive of that value. So in the case of trig functions, you're evaluating with an angle measure, right? So to be even, f of negative theta has to equal f of positive theta. So like evaluating with negative 30 degrees should give you the same as evaluating with positive 30 degrees, okay? To be odd, when you evaluate with a negative angle measure, it should result in the opposite as when you evaluate it with an odd or a positive angle measure, okay? So the functions that are over on the left-hand side, these are the odd functions, okay? These four over here are all odd. So that means that sine of negative theta is equivalent to the negative of sine of positive theta, okay? Cosecant of negative theta would be equal to negative cosecant of positive theta. And it's the same for tangent and cotangent as well. Cosine and secant, these are the only even functions that we have. So that means that cosine of a negative angle measure is equivalent to cosine of the positive of that as well. And then secant of a negative angle measure is equal to secant of the positive of that angle measure. All right. Once again, these properties can just help you to evaluate functions of any angle a little bit quicker, okay? So let's see some examples at play. Simplify using even and odd properties, okay? Well, the cosine function, this is we just said an even function, which means that cosine of negative 30 degrees is equivalent to cosine of positive 30 degrees. And that's equivalent to radical 3 over 2. Okay, again, unit circle could yield that for you, or draw out 30-degree reference angle, 1 radical 3, 2. Cosine is, of course, x over r. Cosecant of negative pi over 4. Well, the cosecant function is odd, which means that this should be equal to the negative of the cosecant of just positive pi over 4, or 45 degrees, okay? So I know that cosecant of pi over 4 is radical 2. I just have to take the negative of that, okay? Let's back up here, verifying. If I'm looking at a 45-degree reference angle here, 1, 1, radical 2, cosecant is y over r, right? So that's, I'm sorry, r over y. So that's radical 2 over 1, and then you just take the negative of it. Okay. All right, now simplify the last two problems here without using a calculator. I'm taking sine squared of 27 degrees and adding it with, and then squaring it and adding that with cosine of 27 degrees squared, okay? So sine squared of 27 degrees plus cosine squared of 27 degrees. Use a Pythagorean identity, that automatically equals 1. You have to make sure that those angle measures are the same, though, in order to use that identity. All right. Now, the second problem is got a lot of identities that can be used here, okay? So we have sine of negative 20 degrees over cosine of 380 degrees plus tangent of 200 degrees, okay? What I don't like right now is that the angle measures for each of those functions, they're all different, okay? But I can use some properties to, some period properties to make those actually all the same, okay? So starting with the fraction there, I'm actually going to use two properties here. Sine of negative 20 degrees is the equivalent of the negative of sine of positive 20 degrees because sine is odd. And then cosine of 380, I'm going to use the fact that cosine has a period of 360 degrees. That means that cosine of 380 could really just be thought of as cosine of 20 degrees because 360, its period, plus 20 gives you the original angle measure of 380 for cosine. And then tangent is got a period of 180 degrees. So that means tangent of 200 can just be thought of as tangent of 20 degrees. Okay. Now I use a quotient identity. Negative sine of 20 over cosine of 20. Since both of those angle measures are the same now, I can say that this is equivalent to the negative of the tangent of 20 degrees. So I'm taking negative tangent of 20, adding it with tangent of 20. Of course, those are going to cancel each other out and result in 0. Okay.